Hello everyone. In this video, we are going to look at some of the math equations that are going to be fundamental to understanding quantitative chemistry. Simply put, in this video, we want to be able to convert between particles, moles, and mass. So let's recall what we've learned so far in this unit. Chemical bonding reactions occur at the particle level, but since we can't measure particles, they're way too small, we need to be able to calculate the number of particles we have by converting a measurement that we make. So for example, we measure the mass of something, and we need to know a way of taking a mass and calculating the number of particles in that mass. Here's our first equation. Our first step is to be able to convert between particles and moles. Remembering, moles are a group of particles, specifically 6.02 times 10 to the 23rd. Our equation here, P equals N multiplied by Na, where particles, or where P represents the number of particles. And we use the term particles because this could mean atoms, could mean ions, it could be molecules, whatever the unit is we're talking about. The lowercase n is always the symbol for moles. And then the capital N and then with the subscript A is Avogadro's number, which is a fixed number of particles per mole, 6.02 times 10 to the 23rd. Let's now switch to the whiteboard and go through some examples. Now, it's great to be able to convert between particles and moles, but that first equation isn't one that's incredibly useful. In fact, chemists rarely talk about the specific number of particles. They're just simply too large to be useful. Kind of a pain to be talking about numbers in the 10 to the power of 23rd. So instead, chemists just talk in terms of moles. And we start to use that term so much that it's easy to forget that when we use the term mole, it's referring to a specific number of particles. Here's our first question. How many carbon dioxide molecules are present if we have 0.2 moles of the gas? So if you're presented with this question, just like any word problem, let's start by writing down what we're given and what we're trying to find. So we're given that number of moles, and moles is given by the symbol N. And recall that the unit for moles is mole, M-O-L. So 0.2 moles. And then I'm trying to find the number of molecules. So whenever you see ions, atoms, molecules, that is referring to the number of particles. So that's what we're trying to find. I'll just put a question mark there. So here's what I'm given. Here's what I'm trying to find. Next up, let's write down the equation that relates those two quantities. So we know that the number of particles is equal to moles multiplied by Avogadro's number. So Avogadro's number is a fixed constant that you need to know. And so we have 6.02 times 10 to the 23rd. In this case, we're talking about molecules, so I'll use that as my particle term. Molecules per mole. Now, there are various ways for doing the calculations for mole math. So you might see that there's some other methods. I like using the equation method. for a few reasons. One, that you're familiar with three variable equations from other math courses and other science courses. So it's a fairly familiar thing to work with. I like to put in the units here because I like to do the canceling of units. So if we have the same unit on the numerator and the denominator, those units cancel, and that gives me the unit of my answer here. So let's calculate this now. If we have 0.2 moles of a substance, we have 1.204 times 10 to the 23 molecules of that substance. Here's our second question. How many moles are there if there are 100 ions of sodium in a sample of water? So here's what I'm giving. I'm given the number of particles. And the particles in this case are ions. I'm asked to find how many moles, the number of moles of sodium. So once again, we have an equation that relates particles and moles. Particles is equal to moles multiplied by Avogadro's number. In this case, I'm trying to find moles, and so I'm going to rearrange this equation to solve for the number of moles. Please come talk to me if going from this step here to this step here, rearranging that equation, was a bit too fast and you're not really sure how I got there. So that's something that you need to be able to do, and I'd like to be able to provide help for that if you are having trouble. So we substitute it in our values, 100 ions. Let's get rid of that. 100 ions. And then Avogadro's number, 6.02 times 10 to the 23 ions per mole. Now we see here once again, we have the ions cancel out and we'll be left with moles. And if we do that calculation, a tiny, tiny number. Remember, a negative, a power of 10 to the negative 22 is a whole bunch of zeros, like 21 zeros, and then 166. So a tiny, tiny fractional number. So there's our answer there with our units included. Let's move on to our more central equation now in chemistry. The most important equation in this unit is this one here. Moles is equal to mass divided by its molar mass. So if we mass a substance and we know what that substance is, and recall from the molar mass video, if we know what a substance is, as in its chemical formula, we can calculate its molar mass. So if we take the mass of something, we divide it by its molar mass, that will give us the number of moles that we have. Let's switch over to the whiteboard and do some examples. Let's look at this first equation using a mass of an element. How many moles are there in 50 grams of mercury? So as with every question, we'll start off by writing out what we're given here. We're given a mass. And we're asked to convert to moles. How many moles? That's what I'm trying to find. And we have an equation which relates those two quantities. Moles is equal to mass divided by the molar mass of that substance. So what substance it is? Mercury, a chemical element. So recall that the molar mass of every chemical element in grams is, so recall, the mass of 1 mole of any chemical element is its atomic mass number in grams. So if I look on the periodic table, the molar mass of mercury is 200.6. Remembering we're going to round these to 1 decimal place. And remember, the molar mass is a mass in grams of 1 mole. So the way we express that is in grams per mole. So when you talk about something per mole, it's the number of grams in 1 mole. That's what we're saying when we're saying grams per mole. 1 mole has 200.6 grams. Okay, next up, let's solve this equation. So if 1 mole has 200 grams, is 1 mole weighs 200 grams, and I only have 50 grams, we should intuitively see that I should have less than 1 mole. That's a good way to check your answer, is to think about what kind of value should I get? Should I be getting something quite large or quite small? 0.25 moles. So about 1/4 of a mole. Remembering that when we just leave it as a short form for mole, that's just talking about a huge number of particles. But it's more convenient to leave it as a mole. Let's look at another example. Let's now look at finding the moles of a compound. In this question, I'm given I have a mass of 100 grams, and the substance I'm talking about is water, H2O. To calculate the molar mass of a compound, we sum the molar masses of all of the atoms which make up that compound. So in water, there are 2 hydrogens, each with a molar mass of 1.0 grams per mole. And I'm getting that off of the periodic table. And 1 oxygen molecule with a molar mass of 16.0 grams per mole. So the molar mass of water is 18.0 grams per mole. And now I can use my equation, which converts mass to moles. 100 grams divided by 18.0 grams per mole So we have 5.56 moles. Let's do one more example of a common calculation. Although we often will measure something and want to know how many moles, you'll see in the latter half of this unit, we also will be often given a molar amount and need to turn that back into a mass. So what is the mass of 0.025 moles of magnesium oxide? What's magnesium oxide? Well, that is MgO. So there's the compound I'm talking about. And I'm given a mole, 0.025 moles. I know the compound, so I can find its molar mass. So magnesium has a molar mass of 24.3 grams per mole, and oxygen has a molar mass of 16.0 grams per mole. So the molar mass of magnesium oxide is 40.3 grams per mole. Now we know that moles is equal to mass over molar mass. So let's rearrange the equation and solve for mass. So the mass is equal to moles times molar mass. 0.025 mole multiplied by 40.3 grams in 1 mole. And the mass will be slightly above 1 gram. So you should be able to, using this equation, solve for any of those three variables by rearranging the mass to molar mass equation. Let's now look at these two equations in a little more of a visual manner. Let's return to the fundamental problem we started off when talking about the mole concept. Chemistry occurs between particles. So in order to carry out chemistry in any sort of precise quantitative manner, we need to know how many particles we're working with. Way too small and way too many of those to measure directly. But what we can measure is something macroscopic about a substance. For example, its mass. In order to measure mass and determine particles, we need to use the conversion factor, which is the mole. And between each of these quantities, particles to moles and moles to mass, we have a calculation. But rather than using that equation again, what I want us to think of is that we have a conversion factor which tells us how much of that something is in 1 mole. For example, our conversion factor between mass and moles is molar mass, because the molar mass tells us how many grams are in 1 mole of that substance. Between particles and mole, our conversion factor was Avogadro's number, because Avogadro's number tells us how many particles are in 1 mole of that substance. And note that both of these conversion factors in green are fixed numerical values. Avogadro's number is fixed absolutely, equal to 6.02 times 10 to the 23 particles per mole. And the molar mass, it's unique to every substance. However, it is fixed for every substance. So if we know what substance we have, we know its molar mass, and that molar mass does not change.